Today we're taking a look at AP Review 12, Rates and Applications, or Rate Applications. This is our second Rate In, Rate Out packet. Um, don't worry, there's more to come in the time for your response. It's a popular question type. Okay, problem number one says there's 700 people in line at the amusement park when things begin. Okay, so the amount at 0 is 700. Once opens, accepts passengers until the park closes 8 hours later. I hope there's nobody in the park 8 hours later when it closes. While there's a line, people move in at a rate of, so rate, move on to a ride at a rate, so the rate in, move on to a ride at which people arrive throughout the day. Okay. Rate, move on to the ride. Okay, people arrive at the ride. Not at the park. So rate out, because they're leaving the line and going onto the ride, is 800 people per hour. And then the rate in is the graph. Okay, I feel like I understand what I'm looking at a little better now. And this is called R of t. So, how many people arrive at the ride between 0 and 3? And this is with calculator. So we want arrive at the ride between 0 and 3. Well, that's integrating from 0 to 3 r of t dt, also known as integrating the graph. I see that each of these boxes has a width of 1 and a height of 200. So I've got an area, well, I know that there's 200 people for each of these boxes. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 full boxes. Here's 2 boxes cut in half, 15. Here's 2 boxes cut in half, 16. So I see 16 times 200, or 3,200 people showed up. How many people arrived? Yes, 3,200 people showed up. Okay, part B. Um, is the number of people waiting in line increasing or decreasing between 2 and 3? Justify your answer. Well, I guess I can do this 2 different ways. The first way, graphically, here's the line y equals 800. And as long as the rate at which people arrive is greater than the rate at which people leave, the line is getting longer. We first saw this on the TCC worksheet, and so that stops happening at 3 p.m. Between 2 and 3, the rate in is still greater than the rate out, and therefore the line is increasing between 2 and 3. And I would actually write those words. Since r of t is greater than 800 on 2 to 3, the line is increasing. Now, there's another less visual way of doing this, where you can build an amount function. You can say a of t minus a of 0 equals the integral from 0 to t of rate in minus rate out dt. And we can say that a of t, therefore, is 700 plus the integral from 0 to t of r minus 800 dt. Now, I want to know, is a, the number of people in line, increasing, the amount of people in line, increasing or decreasing? So I want to look at a prime. That means I need to take the derivative of this. The derivative of this is 0. The derivative of this integral, thanks to FTC1, is just going to be r minus 800. And if I want to know when a prime equals 0, minus 800, that's the same as when is r equal to t, when is r equal to 800. So I would get critical point when r is equal to 800. We see that's at 3 according to the graph. And if I plug in a y value here, so at 2, for example, r has a value of 1200. 1200 minus 800 is positive. And if I plug in a value over here, like 4, r has a value of 400. 400 minus 800 is a negative. And so I can see my line is a maximum at 3 p.m. And because I have this, I know that this line, this amount function, is increasing until we get to 3. So there's two ways of doing the problem. I myself prefer the visual way, but I think the FTC2 way can be really useful. And the justification is the same in either case. Okay. Although I guess if you did it that second way, you might say A is increasing because to the left of t equals 3, a prime is greater than 0. That would also work. But in this case, you have to show the defined a function, remember? A equals 700 plus the integral 0 to t of r minus 800 dt. So that's a second approach. Okay. What about part C? At what time is the line the longest? Oh, well, we figured that out already. In that second way of showing the problem, we saw that we had a max at 3. That was a minus. How many people are in the ride at this time? So we could also talk about this graphically. We know that here, up until 3, there are 3,200 people in line, and 3 times 800, 24 people were served. So 3,200 plus the original 700 people who ran from the gate when the park opened to the ride, minus the 2,400 people who were served at 800 people per hour, gives me 1,500 people in line. That's a lot of people in line. I don't know that I'd wait around for that. Don't forget, we do need to give a reason for why this is longest line. You know, if this crossed back up again, we'd have to do a full candidates test. But this is our only max. And we can defend this, we can justify this, either by defending this justification, defending this max we found when we did the problem, part B, or we could say, hey, R of t is, the line is growing longer as long as R of t is above 800, and that stops happening at 3, therefore the max occurs at t equals 3. So I either want to appeal to the graph or to our derivative of a. Either of those approaches will work here. And part D, write but do not solve an equation involving an integral expression of r whose solution gives the earliest time when there's no longer a line for the ride. Well, and this sort of, this is yet another reason why I like that writing the a function. Remember, we said a was 700 plus, oh, there's a 700 plus this integral. So we could have used this in part B, we could have used this in part C, and now we really need to use this in part D because this is the number of people in line, and they say, what's the earliest time when there's no one in line? So 0 equals 700 plus the integral 0 to t r minus 800 dt, which is really like an easy thing to do if you've already mentally constructed a number of people in line function. You could also say that negative 700 equals 0 to t r minus 800 dt. That could work as well, but this is more students would do this. Okay, so there's problem number 1. And it was with calculator, but I didn't need a calculator to add up some boxes, did I? Okay, problem number 2, also with calculator, says cylindrical can has a radius of 10 millimeters, is used to measure rainfall. Can is initially empty, so the amount at 0 equals 0. The height of the water, I guess the height at the time equal to 0 is 0. The height of the water is measured by S of t, and they give me S prime equals 2 sine 0.03 t plus 1.5. I think I'm going to be using a calculator here. They give me the bounded interval 0 to 60 to check. Okay, so, and this is the rate at which the can is rising. This is the height of the height of the water in the can. So part A, according to the model, what is the height of the water in the can at the end of the 60-day period? So if I integrate, I guess I want to say S of 60 minus S of 0 equals the integral 0 to 60 of S prime dt. Well, S of 0 is 0, and so really I just need this integral from 0 to 60 of S prime dt. Let's take a moment to do this on the calculator. I need to be in radians, and I need to do math, integrate, and we are integrating 2 sine 0.03 x close parentheses plus 1.5 comma x comma 0 comma 60. Okay, and I end up with 171.813 millimeters high at time equal to 60. Show those. Okay. That's A. B. B says, according to the model, what is the average rate of change in the height of water? So the height of the average rate of change in the height of the water will be S of 60 minus S of 0 over 60 minus 0. Or, that's that 171.813 divided by 60, which is 2.863 millimeters per day. You could also think about this as the average value of the rate function. And so do 1 over 60 minus 0, integral 0 to 60 of S prime dt. But we know from FTC2 that this is going to be equal to that. And there's our 1 over 60 minus 0 out in front. So you can understand, mentally perceive the problem in these two different ways. Okay, so there's part B. Part C says, assuming evaporation occurs, no evaporation occurs, at what rate is the volume in the can changing at t equals 7? So here they're saying, what's dV dt at t equals 7? Okay, so I know that the volume is pi r squared height, and I know that the radius is a constant 10, so I know that v equals 100 pi h. Therefore, when I take the derivative with respect to time, I get 100 pi times the derivative of this with respect to time, dh dt. Now, the change in height with respect to time is 100 pi s prime. That's the rate of change in the height. So, we want the rate of change in the height at time equal to 7. So I need s prime of 7. And when I do that, I get 602.218 millimeters cubed per day. Is it day or is it hours? Days. Okay. Great. There's part C. How about part D? Oh my God, there's so many words. During the same 60-day period, rain on Monsoon Mountain accumulates in a can identical to this one, but I imagine at a different rate. At a rate given by m of t. The height is modeled by m. Okay. So m is height at Monsoon Mountain. So m prime is the rate of change in height at Monsoon Mountain. And we're told let d equal m prime minus s prime. Oh, it's kind of like a rate in minus a rate out, except it's the rate at Monsoon Mountain minus the rate at Stormville. And remember, as long as the rate at one place is higher than the rate at the other place, this one will be gaining. Remember the two mice? Apply the intermediate value theorem to D. Okay, well, since m prime and s prime are continuous, IVT says D must pass through all values from d of 0 it helps to read the question. It says, use IVT to justify that there exists a time at which the heights of the water in the two cans are changing at the same rate. So if these are changing at the same rate, then D must be equal to 0. If M and S are changing at the same rate, D equals 0. Okay, now IVT says if these things are continuous, must pass through all values from d of 0 to d of 60. Okay, so if I compute d of 0 on my calculator, that's going back to this function where I'm using m minus s. And so I need to type in that m function, or that, I need the derivative of the m function, which was not given to me. So I think I need to do this. I go to y equals, and I'll type in my s prime function here, 2 sine 0.03 t close parentheses plus 1.5. And then m, which is 1 over 400 times parentheses 3x to the third minus 30x squared plus 330x. And I also want in y3 the derivative of y2, comma x, comma x. Okay, so now I don't actually need that one turned on. Now I've got s and I've got m prime. I mean s prime and m prime. And so here I'm going to do y3 minus y1. And I'm doing this because now when I go to the table, when I go over to my table, I can plug in a 0 and get negative 0.675. And I can plug in a 60 and get 69.3377. I really need to invest in a new color screen. And so since IVT says we must pass through, D must pass through 0 at some point on 0 to 60. Okay, now, this is really important. You're going to lose a point if you don't include that. Okay? Great. So there's problem number 2. Problem number 3. 3 says there's no snow in Jane's driveway at the beginning. Great. The rate at which snow accumulates, so f of t equals the rate in, and that's modeled by 7t e to the cosine t. 6 a.m. is time equal to 6. 6 a.m. t equals 6. All right, how many cubic feet of snow have accumulated in the driveway by 6 a.m.? So for part A on number 3, that's just 0 to, because we started at midnight, didn't we? Feet per hour, t measured in hours since midnight, yes. Of f of t dt. And I do this on my calculator, and I get 142.275 cubic feet. I did, in fact, meet Janet, and she said actually she did measure the amount and built the function based on the amount that she shoveled. So I trust these values. Okay, now part B says, and we've got g of t, which is the rate out function. G equals rate out. Okay. Find the rate of change in volume of snow that accumulates at 8 a.m. Well, so I think here about the amount function again. And so if I build an amount function, we're assuming there's no snow in the driveway at the beginning. Okay, so a of t minus a of 0 equals the integral of rate in minus rate out from 0 to t dx. Okay, so I think about something like this, and what they're asking me is find the rate of change in the volume of snow. This is the volume or amount of snow. And if I want rate of change, I want A prime. So let's take a look here and say amount at 0 is 0. So we just have A equals the integral. And A prime, therefore, is going to be the derivative of this integral, which is f minus g. Okay, so now what we're wondering is at 8 a.m. So we want A prime at 8. That's f of 8 minus g of 8. G of 8, I use the table or the piecewise function and see g of 8 must be 108. F of 8, I'm going to have to plug an 8 into that function. And when I do, I get 48.417. And so A prime of 8, I got negative 59.583 cubic feet per hour. And so the amount is decreasing at t equals 8. And you could say because g of 8 is greater than f of 8, if you like. Or you could say f minus g is less than 0. Either of those will work. Okay. C. C seems easy to a lot of people, but it's a little tricky. Many people got this wrong the year it was given because of C, or they got C wrong because they didn't understand how to deal with this piecewise function properly. Let h of t represent the total amount of snow that she has removed from the driveway. Okay, so remember that g is the rate out. And we know if we integrate the rate out from 0 to t, we're going to get amount removed. Okay? So it says here, express h, the amount removed function, as a piecewise defined function with a domain from 0 to 9. See, here though, the thing is, these are different functions on each of these intervals. And I know integrating a constant is just that constant times b minus a. However, we have a situation here where this constant only works from 6 to 7. And because of that, our h of t function has to look like this. 0 for t between 6 and 0. Then 125, but wait a minute, we only use this after the first 6 hours, so t minus 6. And that's going to be for t between 7 and 6. And then we want to do this third piece, and I'm tempted to say 108 t minus 7. However, I need to include in this amount the stuff that's already been shoveled. Now, conveniently, the first 6 hours, nothing was shoveled. She was asleep. But then between hour 6 and 7, if I plug a 7 in here, 7 minus 6 is 1. 1 times 125 is 125. So she shoveled already 125 cubic feet by 7 a.m. So we need to add that 125 here for 7t less than or equal to 9. Yeah, so here's what I want to say about this. This was 1 point. I'm not going to worry about this 1 point. I mean, literally, it's 1 point. Don't stress about it. You'd probably do your AP score more damage by freaking out about this and saying, I would never think of that. Great, don't think about it. Skip it, move on. Or write something down. The most common thing we saw written down was this, which doesn't make sense because that's the original given function. So really, don't worry about that so much. Okay, and then finally part D, how many cubic feet of snow are in the driveway at 9 a.m.? And so this is where it's good to go back to our amount function. Amount at 9 minus amount at 0 equals the integral from 0 to 9 of r minus g. We know the amount at 0 is 0, and so really all I'm looking for here is the amount at 9. The amount at 9. And I guess I could use my I guess I can use my to think about how much was removed to make that a little easier on my brain, i.e. split this up into 0 to 9 of r minus the integral 0 to 9 of g. I'm going to think about this as, okay, from 0 to 6, she didn't shovel anything. Nothing was removed. From 6 to 7, she removed 125. And from 7 to 9, she worked a little slower. She removed 108 cubic feet per hour, but she did that for 2 hours, 108. And so we get 216 plus 125, or 341 cubic feet removed. And so then a of 9 is going to be this integral from 0 to 9 of r minus 341. And when I do that on the calculator, I get that a of 9 is 26.335 cubic feet remain in the driveway. And they really like when you say cubic feet at 9 a.m. If you don't, you might lose a units point there. Okay, so there's problem 3. Let's take a look at problem 4. 4. 12,000 liter tank of water is filled to capacity. So A of 0 equals 12,000. Water begins to drain out, modeled by R. R equals rate out, where R is given by this piecewise function. Oh, lucky us. I had so little fun with that in the last problem. Is R continuous at t equals 5? Okay, so if R is continuous, then the limit as t approaches 5 of R equals R of 5. Now, in order to find this limit, remember, we need the limit as t heads to 5 from the positive side of R should equal the limit as t approaches 5 from the negative side. So let's plug in a 5 into each of these pieces over here. We're going to plug a 5 in here, and we're going to get 3,000 over 8 from the negative side. 3,000 over 8. And we're going to plug a 5 in here, and so that's 1,000 e to the minus 0.1. And I'm going to pull out a calculator and see if those values are the same. And lo and behold, they're not the same. And so R is not continuous at t equals 5 because the limit as t approaches 5 from the positive does not equal the limit as t approaches 5 from the negative side of R. Okay, and that's part A. What about part B? Find the average rate at which water is draining from the tank from 0 to 8. Okay, so the average rate. So if this is my rate function and I want the average rate, I want the average value of rate, 0 to 8, R dt. I do this, I want to do this on the calculator, except that I've got two different rate functions. Remember how rate was defined as a piecewise function, and so I think I really want to think about this as the integral from 0 to 5 of 600t, don't forget parentheses, divided by, don't forget parentheses, dt, plus the integral from 5 to 8 of 1000 e to the negative 0.2 t dt. Oh, and that last problem, 5 times 0.2 is going to be negative, so e to the negative 1. 1000 e to the negative 1, or 1000 over e. Was that equal to 3000 over 8? And the answer was no. Okay, so this is my setup. I'm going to get a point for this setup, so I want to show this setup. This would not be sufficient because they want to see me understanding that I'm dealing with a piecewise function here. And the answer is 258.052. And I'm looking for the average value of rate, and the rate units are liters per hour. Okay, that's the average rate at which water leaks out, or water is draining out. So there's part B. Part C, find R prime of 3. R prime of 3. Well, this problem is with calculator, and they give me R, and so I just need to take R equals 600t, t plus 3. I need to do, and no, I'm not going to say that. Look, all you have to write is R prime of 3 equals the value. But over here in your calculator, you want the derivative of that. So parentheses 600x divided by, don't forget to close that parenthesis, x plus 3. And then I want the derivative of that. I don't need this. And I want to go over to table and evaluate the derivative at 3. So there's the function at 3, and there's the derivative of 3. And I get 50 liters per hour. Per hour. There we go. It seems like the amount is increasing. Remember, R was a rate function in liters per hour. So R prime is the change in R over the change in time. It's liters per hour, change in R, over change in time, hours. So there's my R prime, 50 liters per hour. And what does that mean? The rate at which water is draining at t equals 3 is changing, that's a safe word, changing at 50 liters per hour. Great. I would not use 50 liters per hour every hour. Or we could, I guess, say increasing. That would be a safe word too. Okay, so there's part C. Now, what about part D? Part D says, and my guess is this is where I'm going to be using FTC part 2. And so I want to think about, oh, and remember the amount drained out was a positive number. So I'm going to have to subtract that amount that drains out from the amount there is. Let's see what we say here. Write but do not solve an equation involving an integral that finds the time A when the amount of water in the tank is 9,000 liters. Okay, so so I want 12,000 minus the integral from 0 to A of R of t dt to equal 9,000. So starting amount, take away the positive number that is how much drained to equal 9,000. And I guess we could subtract and say the integral from 0 to A of R of t dt should equal negative 3,000 divided by negative is 3,000. That would also work. But most students wrote something like this who got credit for it. Okay, there's part D for number 4. How about number 5? 5 says, oh, the mighty cable company. Yeah, this is another problem that had a part that drove some kids crazy. And I would definitely think about units here. Let's think about what's going on. 0 to 31, the rate of, no, that's the next one. Sells cable for $120 per meter. For a fixed length, the cost of producing a portion of cable varies with the distance from the beginning of the cable. Mighty reports that the cost to produce a portion of the cable, that is X meters from the beginning of the cable, right? And so if here's the beginning of the cable and we want to make something that's 10 meters, it's going to cost a different amount per meter than if we make something that is 15 meters long. To make a longer cable costs more money, not just for the extra 5 meters. It's not a linear relationship. It's this becomes a scientifically and engineering more challenging prospect to draw a longer cable, and therefore we need this relationship that they give us. They say that the cost to produce a cable X meters long, so I want to say C of X equals 6 square root of X. Dollars per meter. Now notice dollars per meter. This cost function in dollars per meter is really our rate function. And I'm going to be integrating this rate at some point to get dollars. Okay, let's move on and see what else we know. Profit is defined as the difference in the amount of money received by selling the cable and cost of the cable. And I guess this is the rate out. And the rate in is that $120 per meter that we get when we sell the cable. Okay, so find the profit on the sale of a 25-meter cable. Well, profit equals rate in, the revenue, of 25 minus, I'm sorry, I'm looking for profit. Yeah, these are our rates though, and profit is not this. I need the antiderivatives of this. Let me try again. Profit is the difference between the amount in amount in minus amount out. The amount in is the integral of rate in minus the amount out is the integral of c of x. And we're integrating from 0 to 25 in each case. So that's the amount in, that's the amount out, and this is P, and I get a calculator. So after this setup, I'm not going to try and put in 125 here, 0 to 25, sorry, 120, and then say, okay, I know the antiderivative of this is 120x from 0 to 25. I'm not going to do this stuff. I'm just going to save my time and go to my calculator and punch this in, and I'm going to get $2,500 in profit for a 25-meter cable. And if you think that's a lot of money, try and make your own 25-meter cable and see how much time and effort that costs you. I won't begrudge them $2,500 in profit for making me a cable that's more than 75 feet long. Okay, there's part A. Part B. Part B says, using correct units, explain the meaning of 25 to 30, 6 square root of x dx. Well, this is the rate in dollars per hour, and these are dollars per meter, and these are meters. And so we could say, I wish I had a thing here like big C. So I want to say the cost of a 30-meter cable minus the cost of a 25-meter cable. That's what I'm getting here when I integrate that rate. You know, if we try something a little more general, big F of B minus big F of A equals the integral from A to B of f dx, where f equals big F prime. So if I integrate that rate, I'm going to get this change in amount. And so for us, this is dollars per meter times meters, and so I'm getting dollars. This is dollars at B, so the cost of a 30-meter cable. This is dollars at A, therefore the cost of a 25-meter cable. So what we're finding here is the difference in cost to make a 30-meter cable rather than a 25-meter cable. Or you could write something like this. That would be sufficient as well. And using correct units, cost in dollars. Do we need to find a value here? I don't think we need to find a value here. You know, you could also describe this as how much more, because when we find this difference, it's going to be the difference between making this one and this one. And so you could say how much more it costs a 30-meter cable than making a 25-meter cable. Okay, part C. Write an expression involving integral that represents profit in the sale of cable that is 12 long. All right, so we know that we can write this profit as the integral of 120 minus 6 square root x dx, and we want from 0 to k. Do we have to do anything beyond that? I don't think so. Write an expression involving an integral that represents profit. So this is the total amount that we get coming in when we integrate rate in, And when we integrate rate out, that's the total cost to us to make the thing. And the difference between the money in and the money out is going to be our profit. So P of K. All right. And then finally, part D. Part D says, find the maximum profit. Okay, so I've got this profit function, and now I want P prime. I want to find out when P prime equals 0. Luckily, I can use the FTC part 1 and take the derivative of this. And so I'm going to get P prime equals 120 minus 6 root K. And I want P prime equal to 0. So that's this. And that's 6 root K equals 120. Or root K equals 20. And then many students took the square root of both sides here, but you want to undo square root, so please remember to square both sides. So K equals 400. So I get a critical point at 400. Presumably, I don't have any profit if I make no cable. So I'm going to put a 0 over here. And I'm going to put a value into P prime, something that I can easily take the square root of, like 100. So square root of 100 is 10. 6 times 10 is 60. That's going to be positive. And if I put in a number that I can easily take the square root of, like 900, that'll be 30 times 6, which is 180. 120 minus 180 is negative. And so really, my profit is maximized when I make 400-meter cables. I really don't want to make a cable that's longer than 400 or my profit is going to start to sag. I'll probably make such a thing, but profit will be less. Okay, so max profit is maximized at 400. Justify your answer. Profit is maximized by making a cable 400 meters long because to the left of K equals 400, P prime is greater than 0, and to the right of K equals 400, P prime is less than 0. Remember when that seemed really hard to you, just to keep it in your brain what we were talking about when we were talking about this justification sentence? And it's so easy and natural for you now. Good job. Okay. Problem 6. Problem 6. For 0 to 31, the rate of change in the number of mosquitoes is modeled by big R. Big R equals mosquitoes per day. There are, at time equal to 0, 1,000 mosquitoes. And so I can build my amount function, A of t minus A of 0, not 1,000. 0 equals the integral 0 to t of r of t dt. R of x dx. Remember, dummy variable. Okay, so I've got my amount function that I'm probably going to need. And they've given me this rate function. I get to use a calculator. Let's go. Part A, show that the number of mosquitoes is increasing at time equal to 6. So the amount function, I want to show that the amount function is increasing, so I want A prime. And A prime is just the derivative. The derivative of a constant is 0. And the derivative of this integral is r of t. And so at time equal to 6, I want big R of 6. I'm just going to pull out my calculator, type in R of t, get big R at 6, and that turns out to be 4.438. Since big R of 6 is greater than 0, amount is increasing at t equals 6. Don't forget that. amount or number of mosquitoes. Okay, so where do we go from there? Part B. At time equal to 6, uh, at time equal to 6, is the number of mosquitoes increasing at an increasing rate, or is the number of mosquitoes increasing at a decreasing rate? Well, I want a double prime of 6 then. And to find a double prime of 6, that's r prime of 6. So I'm going to do n deriv of y1 to find this, and I get negative 1.913. And since a double prime of 6 equals r prime of 6 is less than 0, we say increasing because of this at a, and because of this, decreasing rate. And remember, increasing at a decreasing rate looks like that. Okay? So what's next? Part C. Part C says, according to the model, how many mosquitoes will be in the island of 31? So we go back to our amount function, a of 31 minus a of 0 equals the integral from 0 to 31 r of t dt. And so a of 31 is going to be, how many did we start with? 1,000 plus the integral 0 to 31 r of t dt. Please actually write this out. This is worth lots of points on the AP exam. Just don't not write that. This is you really need to show the notation. Don't do it in your head. Reach for FTC2. Build that amount function. Show them you know calculus. This is a bulletproof way to earn 2 points. And then pull out your calculator and evaluate this. I ended up with a of 31 equals 964.335, or approximately 964 mosquitoes at t equals 31. And those are days, something. Yes, days. Okay. And finally, part D, to the nearest whole number. Oh, to the nearest whole number. That's why we did 964. To the nearest whole number, what is the maximum number of mosquitoes? Okay, so again, I reach for this amount function, and I say that a of t equals 1,000 plus 0 to t of r dx. I want to know when the amount is a maximum, so I want a prime. So I take the derivative of this to get a prime, which means I take the derivative of that, which is 0, and I take the derivative of that, which is r of t. And so I'm looking to find out when r of t equals 0. Well, if I go about graphing r of t on my calculator, r of t is given by this function 5 square root close parentheses, mash some more things, Mr. Kukla, cosine x divided by 5. Okay, so if I graph that function on 0 to 31, and y minimum, I can't imagine having a negative number, but oh, it's a rate function, so I can't have a negative rate. I'm going to go negative 10 to 10, because really I'm just looking for x-intercepts. I see 1, 0. I see another 0. Okay, and so if I do second calculate intercept, I find those points to be t equals 7.85398. and t equals 23.5619. Okay, so I need to do a candidates test here to find the maximum. Remember to include 0 and 31. A of 0 is 1,000, and A of 31 equals 964. We found those out already. But we also need A of 7.85398, and we need A of 23.5619. And remember, this is our A function. And so what we're doing for this is we're doing 1,000 plus the integral 0 to 7.854 r dt. And I got, when I did that, 1,039.357. And here, 1,000 plus the integral 0 to 23.562 r dt. I ended up with 964.355. Oh, sorry. Sorry. Didn't compute that because it was wrong. I can compute it now. Yeah, so looking at the graph, I said, oh, look, this is a graph of R, and R is the rate. So rate, the amount is a maximum here because rate goes from positive to negative, and rate is a minimum here. I'm sorry, amount is a minimum here because rate goes from negative to positive. But I can certainly integrate this to get this value to have a complete candidates test. Remember, our r of t function here is what I've typed into y1. So y1, comma x, comma 0, comma 23.5619. And I end up with a number less than 1,000, I'm sure. Oh, it's still thinking. Thank you so much for all your hard work. It would be ever so much harder for me to do this problem. Wow, it's still thinking. I kind of want to start looking at the next problem. Oh, look, there we go. So we've got 842 to the nearest mosquito, it says, right? Yeah. I say that's the maximum number of mosquitoes. Max mosquitoes equals 1039 at t equals 7.854 days according to the candidates test. Okay. Number 7. Just 2 more problems to go. All right, Karen rides her bicycle along a straight line from home to school, goes from 0 to 12. Okay, so let's think about what's happening here before we actually read the problems. This is the rate at which she rides her bike, from 0 to 12 minutes. Her rate is 0. She gets on the bike, she starts biking towards school, then she slows down and stops. And then she bikes the same amount back in the opposite direction. My guess is that Karen forgot her homework and she had to go back home. Oh, look, no velocity. The bike is not moving. She spent a minute grabbing her homework, and then, she's now going to be late to school. And so, look, the rate is steeper. She bikes faster than she did originally. She bikes faster to make up that lost time. And so this area represents the distance from her house to the school. All right, I feel like I know what's going on here. Let's see. Find the acceleration of the bicycle at 7.5. So 7.5 is here, and 7.5 would be the slope of this line segment. this line segment goes from point 3 minus, no, goes, I want velocity at 7 minus velocity at 6 over 7 minus 6. Velocity at 7 is 0.2. Velocity at 6 is 0.3 over 1, which is negative 0.1 over 1. Okay, and the units here are miles per minute, and these are minutes down here. And indicate units of measure. I did that. Okay, I feel comfortable with that. Negative 0.1 miles per minute per minute. Fabulous. Part A. Part B. So it's just the slope of that line segment, because the slope at any point on that line segment will be the same. So I'm just finding the slope between these 2 points. Okay, part B. What's up with Karen? Using correct units, explain the meaning of the integral 0 to 12, absolute value v of t dt. And that is total distance in miles. It really is miles, isn't it? V for velocity in miles per minute, yes. Total distance in miles traveled during the 12-minute interval. I don't want to use a word like trip or bike to school because she started biking to school and then she stopped and went back home. So I'm just going to be a little vague and say that during the 12-minute interval. I do want to talk about the 12 minutes, and I do want to talk about the miles. Please make sure you address that. How do I know that? Because if I integrate the absolute value of velocity, I'm talking about, flat. I'm talking about integrating speed. And so this is going to give me, they travel this much and this much and this much. All of these are positive. I add up all those positives and I'm going to get the total distance traveled. This, integrating velocity, is the net change in position as opposed to total distance traveled, because I'd have to do this positive area minus this negative area. But here we're doing absolute value, and when we integrate speed, we get total distance traveled. Okay, part C says, shortly after leaving home, she realizes she left her calculus homework at home. She returns to get it. At what time does she turn around to go back home? Oh, she turns around at t equals 2 when velocity goes from v greater than 0 to v less than 0. Okay, part D. Larry also rides a bicycle on the straight road. His velocity is modeled by this other function, pi over 15 sine pi over 12t, where w is miles per minute. So this is again a rate function, miles per minute. And he's also doing 0 to 12. Who lives closer to school, Karen or Larry? Well, so if we, Larry didn't go back. So we want to compare the integral of Karen's rate, which I guess we're calling v, from 5 to 12 dt, and we want to compare that with Larry's w of t from 0 to 12 dt, and see which one is bigger. I compute that she traveled 1.4 miles, right? Because each of these boxes is zero point 0.1 times 1 or 0.1. So I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 12 and a half. And then I've got 3 boxes cut in half. 3 cut in half plus 1 half plus 12. And so that's a total of 14 boxes. And so 14 times 0.1, the area of each box is 1.4 miles. That's Karen. And Larry, when we integrate this, I get Larry's is 1.6. So Larry lives further. Who lives closer? Karen lives 0.2 miles closer than Larry. Okay, so there's problem number 7. That didn't feel so bad. And finally, problem number 8. Let's see how that one goes. The figure shows an above-ground swimming pool with a radius of 12 and a height of 4. Pool contains 1,000 cubic feet of water at time equal to 0. So A of 0 equals 1,000, and that's cubic feet. Yes, during the interval 0 to 12, water is pumped into the pool at P of TP equals rate in, and those are cubic feet per hour. And then the table gives values during the same interval. Oh no, water is leaking from the pool. Don't worry, it's not a leak. It's just kids splashing around. R equals the rate out. Okay, so what are we asked to do here? Use a midpoint Riemann sum with 3 subintervals of equal length the total amount of water that was pumped into the pool on 0 to 12. All right, so we've got this table here, and we want 3 subintervals of equal length. So B minus A over 3, right? We're doing B minus A over N. So that gives me a subinterval width of 4. So 0 to 4. Because I'm doing a midpoint Riemann sum, I go to the middle of that subinterval and grab the height there. So subinterval width of 4 times 46 plus a subinterval width of 4 times, now the next interval goes from 4 to 8, and halfway across that interval is 6, so I want 57, plus the next subinterval width is 4 from 8 to 12. I go halfway across that interval to 10 and pick up 62. And you could certainly have written this as 46 plus 57 plus 62 with the 4 factored out. This represents the total amount that was pumped in during the 12, what are my units? Hours. Pumped, and these are cubic feet pumped in during the hours from 0 to 12. Okay, if you want an actual number for this, I got 660 cubic feet. And I find I often have to use a number like this later on in the problem, so to me it's worth figuring this out. And I'm given a calculator, so it's not that big a deal. But here's part A. Part B. Part B says, calculate the amount of water that leaked out of the pool during the interval. Well, that's just going to be the integral from 0 to 12 of this R function. And when I do that on my calculator, I get 225.594 cubic feet. Hey kids, stop splashing around in there. All right. So then in part C, use the results from A and B to approximate the volume of the pool at t equals 12. Okay, so I know the amount in the pool at time t minus the amount 0 equals the integral of the rate in minus the rate out, dx, 0 to t. Okay, and so we're talking about 12. So a of 12 minus the amount at 0. We started off with 1,000 equals the integral from 0 to 12 of p minus the integral 0 to 12 of r. Well, we found this in part A. This was 660. We found this in part B. This was 225.594. And we want to add 1,000 to find A of 12. And I come up with 1434.406 cubic feet at t equals 12. And again, these are hours. Okay, there's part C. How about part D? Find the rate at which the volume is increasing at t equals 8. Okay, so here's my amount function, and I want the rate at which volume is changing. So I want A prime. I take the derivative of this. The derivative of a constant is 0. The derivative of this integral is just going to be p minus r. P of t minus r of t. So we want to know, find the rate at which the pool is increasing at 8. I want A prime of 8, which is p of 8 minus r of 8. That's 60 minus 16.758, or 43.2419 cubic feet per hour. Now, this is a change in the rate. How fast is the water level in the pool rising? That's a different question. This is cubic feet per hour. Remember in chapter 5, how would I name that calculously? That's dV dt. And what are they asking me here? What is the change in water level? They want dH dt. So I have to do a related rates problem now. All right, let's go related rates. So we know V equals pi r squared h. Radius is a constant. Radius is a constant 12, so 144 pi h. And then I take the derivative of both sides with respect to time, dH dt. I plug in my 43.2419, 144 pi dH dt. I divide both sides by 144 pi, and I get dH dt equals 0.0956 feet, not cubic feet, it's height, so that's feet per hour. All right, there's part D. Excellent. Welcome to being done with AP Review 12. Really, they do a lot of these rate in, rate out problems. This is our second packet, and there's still more of these problems coming your way. I would count on something like this on the AP exam. Have a great day, everyone.